Okay, so this is a nice sort of application, brings up some college algebra skills. We're going to be given certain numbers in the pattern, and we want to work backwards and figure out what the first number is, and then what the general pattern of the sequence is. Okay, I'm told the 11th number is 52, and the 19th number is 92. So somewhere in this pattern, I don't know what the first number is, I don't know what the second number is, I don't know what the third number is, okay, dot, dot, dot. Somewhere I've got the 11th number, and it's 52, and then I've got the 19th number, and it's 92. And the idea is, can I work backwards and get the first number? And then I can use that formula that we looked at earlier to generate the nth term. Okay. So one thing I'm going to do is let's look at that nth number formula for a second. It's the first number plus n minus 1 times that constant difference. Well, let me fill in what I know about the 11th number. So I know that when n is 11, so when n is 11, I know 52 equals the first number plus 11 minus 1 times that constant difference. Okay. I'm going to fill in the same thing for the 19th number. When n is 19, I get 92 equals the first number plus 19 minus 1 times that common difference. Well, let me simplify that real quick. So that's 52, 11 minus 1 is 10, and this is 92 equals a plus 18d. Okay, and now I've got two equations and two variables, and so I can use what's called a system of equations to solve for the missing information. This might be something you'd show, middle school students. Definitely would show middle school students this type of math. So 52 equals a plus 10d, and 92 equals a plus 18d. So what I'm going to do is I'm going to subtract those two equations. So I get negative 40. The a's don't disappear because a minus a is gone. And then 10 minus 18. 10 minus 18 is, let's see, negative 8d. And so then I want to divide by negative 8. And so our common difference here is 5. And then I can go back into one of our equations. So 52a plus 10 times 5. And I can solve for that first number. So that's a plus 50. So that means our first number has to be 2. Okay, so that answers one of our questions, is that the first term is 2. And then I can use that nth term formula. So nth term would be a to the n equals a plus n minus 1 times that common difference. So nth term would be 2 plus n minus 1 times 5. And then I can simplify, distribute, and simplify, combine like terms. Sorry, a to the n equals 2 plus 5n minus 5. And I see some like terms. 5n minus 3. So there's our nth term formula there. Okay, so it's a nice visual pattern you might introduce in lower grades and kind of make your students think. Find the pattern and the number of matchsticks required to continue this pattern. Well, we have in the first box, we have 4 of them. In the second box, we have the original 4 plus 3 more, so we have 7. In the third one, we have the original 4 plus 3 more plus 3 more, so that's 10. Well, let's stop and look for a second. What do we notice is happening here? Aren't we adding 3 every time? Right? And so if the pattern continues, I should get 13. So 1, 2, 3, 4 plus another 3 each time. So yeah, 9 plus 4 is 13. So that's our pattern. We're looking at an arithmetic sequence where the first number is 4, and that common difference is 3. So, write that out. 4 plus n minus 1 times 3. Alright, so 4 plus 3n minus 3, and I can combine like terms, so that would be 3n plus 1. So you tell me what pattern in this matchstick we have, I can tell you what the required pattern is. Let's do another one of these. The diagrams shown below the molecular structure of alkalines, class of hydrocarbons. So we're doing some chemistry here. C represents the carbon atom, H represents the hydrogen. A connecting segment shows chemical bonds. Okay, so we want to know as how many hydrogens versus how many carbons. Okay, so notice, sort of interesting, we got a pattern here. The C's is increased by 1, so 1C, 2C, 3C, kind of like the first number, the second number, the third number. So really, we just need to worry about the H's. So we start off with how many H's? We got 4 H's in the first one. Then we have 6 H's. Then we have, let's see, so we got 8 H's. What do we notice? We notice we're adding 2 every time, right? So what would our pattern be? Well, it's an arithmetic sequence based on adding, and I'm adding, the first number is 4, and our common difference is 2. So our nth term would be 4 plus n minus 1 times 2. And I can combine like terms. Let's see, so that's 2n minus 2. So that would be 2n plus 2. So you tell me how many carbons there are, so that would be the n. Then my little formula here will tell you how many hydrogen there is based off that. Okay, geometric sequence is based off multiplying. So in arithmetic, we looked at adding a constant term. In geometric, we're looking at multiplying a constant term. And so the formula way to describe this is we have R as a common ratio. That's that thing that we are, oops, sorry about that. It's that thing that we are multiplying by. And so to generate the terms of the pattern, we take the first number for the first pattern. The second one, we take that common ratio times the first number. For the third term, we square the common ratio, multiply it by the first. Okay, and then in the nth term, in the general n position, we have that lovely formula there, where we're taking the common ratio and we're taking the exponent one less than the position we want. All right, so let's kind of work that out with some numbers and kind of see this in real life how that works. So here we're given that the first number of a pattern is 2 and the common ratio is 3. So in the first position we have 2. Then in the second position, okay, so we're going to take 2 times the common ratio. So now we've got 6. In the third position, we're going to take that 6. Well, let me show you a couple different ways to do this. Take 2 times 3 times another 3, or 2 times 3 squared. So notice our exponent is 1 less than the position in the pattern. And then this would be 18. So we could have just 2 times 3, so 2 times 9 is 18, or we could have just taken that 6 times 3 and gotten 18. Okay, the fourth number would be 2 times, how many 3's? 3 of them. So 3 cubed, which is 27. So 27 times 2 would be 54. Or I could have just taken 18 times 3. And that also would have given me the 54. Okay, the nth term. So the nth term, just fill in what we know. We know the first number is 2, times that common ratio of n minus 1. And in this case, there's not really too much we can simplify for that. Okay, so this is another illustration why that nth term formula is just so powerful in that we've got the first couple of terms of a pattern and we want to generate the nth term. Now I know we're talking about geometric sequences, but let's kind of consider whether it's geometric, arithmetic, or something else. So how do I go from 2 to 4? Well, I could do 2 plus 2 to get the 4, or I could do 2 times 2 to get the 4, right? So I don't have any information there, but how do I go from 4 to 8? Well, 4 to 8 is 4 plus 4, or 4 times 2, right? Okay, but if it's arithmetic, it would be a common difference. That's not a common difference. It's not the same number being added every time. But if it's a geometric, it would be a common ratio. And so do you notice how you're multiplying by that same constant amount each time? So our first number is the 2 they give us, and the common ratio is, well, the number we figured out was 2. So the nth term would be the first number times the common ratio to the n minus 1 power. So the 30th number would be 2 times 2 to the 30 minus 1, or 2 times 2 to the 29th. Now, that definitely is a good calculator question. I don't think anyone should know what 2 to the 29th power is off the top of their head. So we end up with this really big number, 107,374, 1824. So what is that? 1,073,741,824. All right. All right, so let's look at some other sequences that don't fit arithmetic or geometric. These are kind of some fun ones to play with. At least, kids kind of get excited when the first time they see this. Let's start with what's called a triangular number. Okay, you'll kind of see why in a second. So 1, 3, I'm adding an extra layer to the triangle, so that's 6, 2, 3, 4, 1, 2, 3, 1, 2, 1, and that gives me 10. So any pattern that fits this format we call triangular. Similarly, we have what are called the square numbers. It's kind of where we get our term perfect squares, but we have 1. So anything, so 4. And then we have 9. I'll do one more. And that's 16. So anytime we can visualize these things with squares, then or shapes, then we call it after that particular term.